Hey everyone, and welcome back to the channel. It's episode 5 of our Zindi walkthrough series, where we're tackling the scarce Root Volume Estimation challenge. If you've been following along, you know we've already visualized those tricky segmentation masks, improved a CNN benchmark, dove into YOLO for segmentation, and even revealed the full plant structures. But today, we're taking a huge leap forward. We're going to explore how to get segmentation masks of the entire plant, and get this, in a zero-shot manner. The challenge with this competition is that the provided segmentation labels are severely limited. Only a small subset of plants have labels, and many labels are just for one side of the plant, missing the other, meaning we don't have full plant labels. That's why today, we're tackling zero-shot segmentation, which means no specific training for this task. We're going to harness the power of Meta AI's SAM, the Segment Anything model. This is a great model if your task is to segment images, but have limited labels or no label at all. It's applicable to many tasks in computer vision. Before we dive into the code, let's actually see SAM in action. I've got the Segment Anything demo website open here, and I uploaded one of the images from our competition. Next, select the Everything mode, which, as the name suggests, will try to segment everything it can find in the image. Wow, look at that! Without any specific training on root images, SAM has done a remarkable job of identifying and outlining the individual root segments. You can see how it's picked out pretty much all the distinct root parts, giving each one a different colored mask. And see how a blue line marks the contour of each mask. This is incredibly promising. This online demo shows the potential, but for our competition, and for more control and customization, we need to run this locally. All right, let's jump into the code. The first thing we'll see is the installation step. We're using pip to install the Segment Anything package directly from Facebook Research's GitHub repository. This gives us all the tools we need to work with SAM. Next, we import our libraries: Torch for deep learning, Segment Anything, of course, CV2 for image processing, and other helpful packages. Now, a crucial step, you'll need to download the SAM checkpoint. There's a link provided, and it's pretty big, so make sure you have a stable internet connection. Okay, here's where the magic starts. We're defining which device we want to use. If you have a GPU, it'll use that, otherwise it'll default to the CPU. We specify the model type, VITH, which stands for Vision Transformer Huge. Vision transformers are becoming increasingly popular in computer vision, often outperforming traditional convolutional neural networks. And of course, we point to the checkpoint path where we downloaded that massive file. Then, we load the model and send it to our chosen device. We then create a mask generator using SAM Automatic Mask Generator. This is the object that will actually do the heavy lifting of finding all the segments in our image. Now for the fun part. We choose an image from our dataset. We read it in BGR format, blue, green, red. But for SAM, we need it in RGB format, so we do a quick color conversion. And then, the moment of truth, we call Mask Generator and pass in our RGB image. It takes a few seconds. It is leveraging all the power of its pre-training and generates not a single mask, but multiple masks. We are using the Segment Everything model to predict everything. This Segment Everything approach is a key feature of SAM, allowing it to be so versatile. If we check the length of the result, we see it's not just one mask, it's many. Each item in this list represents a potential segment, a region of the image that SAM thinks is distinct. Each region has segmentation mask, bounding box, IOU score, etc. The output is impressive, but it's a bit hard to visualize what's going on with just raw data. So, let's create a helpful function called Draw Mask Contours. This function takes our original image and a list of masks. It then uses CV2, find contours, to find the outlines of each masked region and draws those contours, in green, on the image. Finally, it displays the result with all the masks over the image. And the result is great. SAM has done an incredible job of outlining pretty much every distinct part of the plant, all without any specific training on plant images. Remember from episode 4, we showed how we can reconstruct the full plants, and to truly see that complete structure, we'd need to take the right side image, rotate it 180 degrees, and place it above the left side image. Sam is giving us a pathway to do segmentation on the entire plant structure. This, my friends, is the power of zero-shot learning. Now, why is this so cool, even if you're not in this specific competition? Because it demonstrates the incredible generalization ability of these large, pre-trained models. Sam was trained on a massive dataset of diverse images, and it has learned to identify visual patterns so effectively that it can segment things it's never explicitly seen before. This has huge implications for all sorts of image analysis tasks. Imagine using this for medical imaging, quickly segmenting organs or tumors, satellite imagery, identifying different land cover types, robotics, helping robots understand and interact with their environment, photography, edit only specific items in a photo easily. The possibilities are endless. This concept of zero-shot learning is a major trend in AI, allowing us to tackle problems with limited or no labeled data, which is a common bottleneck in many real-world applications. This episode, we showed how to obtain segmentations of the full plant in zero-shot manner. That's it for today's episode. I hope you found this deep dive into SAM and zero-shot segmentation as exciting as I did. Don't forget to like, subscribe, and hit that notification bell so you don't miss the next video in our Zindi Challenge series and all our other AI and machine learning content. Keep exploring, keep learning, and I'll see you in the next video.